Thank you for the kind presentation, and I want to thank the organizers for inviting me. It's an honor for me to give a talk on occasion of Shigui's birthday. Happy birthday. Shigui and I don't think we have collaborated. I don't think we have a single paper together, but probably we read each other papers because we work in adjacent and overlapping areas. So there is a lot in common, and this talk is still celebrating his work. So as it was announced, I will talk about optimal control of an immuno-epidemiological model of HIV and opioid epidemics. Immuno-epidemiological models are also age-structured models, just like Glenn introduced a few minutes ago or half an hour ago. But they are somewhat of a different kind. And I will talk about these two epidemics, HIV, which has been an epidemic since the 80s, and opioid epidemic, which has been around for a while, but in the past 20 years or so has become particularly bad. And I was advised to stay here and point with this nice, pretty hand. Do you see it? Yes. So that I can point to whatever I want to point to, and the laser pointer is very, very pale and probably not visible on the screen. So I will start with an introduction, and I will talk about HIV as an epidemic itself, and I'll talk about opioid epidemic as an epidemic itself, and I will talk about how these two epidemics are intertwined. And then I will introduce the opioid HIV model, which is, as I said, a multi-scale model. So it will consist of several components. And then I'll show you how we parameterize opioid HIV model. These models are not easy to parameterize from data unless you fit actually to the data. And then I will introduce a modification of the original opioid HIV model, a modification that involves 4 controls. 2 of them are on the within host level and 2 of them on the between host level. And then I will show you what optimal control scenarios we explored. We explored 6 different scenarios. And in the summary of the results, I will tell you which scenario we found to be the best. So in the last 20 years, the use and abuse of opioids in general and heroin in particular has increased immensely all over the world. And the death rate of opioids has been rising. And this graph on the right shows the deaths from drug overdose starting from 1999 through 2021. And you can see that in 1999, there were about 8,000 deaths from opioids, but in 2021 there were 106,000, and actually there is data now for 2022, and in 2022 the number of deaths still increased to 107,000 deaths. So the death rate is really alarming, and it has alarmed many officials to act on this epidemic. So the opioid epidemic has become a health crisis in the United States, and unfortunately, this is not just a United States problem. The data is from the United States, but other countries are not doing much better with respect to this. And heroin accounts for about 1/3 of the drug overdose deaths. HIV is an epidemic that we are all familiar with. It has been around since the early 1980s, so 40 years. And currently, there are about 1.2 million people in the United States living with HIV. So the people living with HIV is the red curve. These are the data which have been interpolated to form a continuous curve. And you can see that the number of people living with HIV has been continuously increasing throughout the years. And this is still the trend, even though the data stop at 2008, that trend still continues. There are reasons for that, but that's the trend. On the other hand, the death rate from AIDS is declining due to much improved treatment. So in the 1990s, in the mid-1990s, the highly active antiretroviral therapy was introduced. And as you can see, it was instrumental to bring an increasing death rate to a decreasing death rate. And the death rate is kind of stalling a little bit in the recent years, but it's continuing to decrease. The incidence of HIV, I don't know whether you know what incidence is, but the incidence is the number of new cases of HIV. So this is also declining, and this is not pictured on this figure. So the two epidemics, we have an HIV epidemic and an opioid epidemic, and they're not unrelated. I mean, they have quite a bit of points where they touch. So, for instance, one reason why they are related is that opioid use increases the chance of getting HIV. And the two epidemics are intertwined because injecting drug users, often abbreviated as IDUs, may share a needle with an HIV-infected person. And 1 in 10 individuals who get HIV is through injecting drug use. Drug use lowers inhibitions and leads to behaviors which can easily lead to acquiring HIV. So that is another reason for drug use, for using the drugs to increase the number of HIV cases. HIV-infected individuals who use drugs have poor health status, and the co-infections, so when there are two epidemics, and I'll talk about this in the modeling component in a minute, when we are considering them together, and when a single individual can both have HIV and be a drug user, that leads to something called a co-infection of opioid use and HIV. That co-infection leads faster to death. So opioid use modeling is a little bit newer. It doesn't go as far back as HIV modeling, and people discovered that modeling heroin addiction and spread can be done with classical epidemic models. And modeling HIV and opioid epidemics leads to a co-infection type of model. This is what I just spoke about. So co-infection models is when you have two different diseases interacting in some way. And this way in the model that I will present in a minute is that some individuals can have both opioid addiction and HIV. Co-infection models are not new. They have been around for, I don't know, another 20 years. They are typically investigated for two strains or two different diseases. Investigating co-infection models for two different diseases has been very popular in the recent years, with many disease combinations having been looked at. However, modeling opioid dynamics in a population is relatively new, and we study here for the first time the co-infection and opioid use. We have been studying it for a while now, maybe 4 or 5 years, maybe more. When we started, that was a new approach to studying the co-infection of HIV and opioid addiction, particularly on population level. So now I will introduce our model. So as I said, our model is a multi-scale model. And multi-scale models, this is a general diagram of multi-scale models that comes from trends in ecology and evolution. This is not the diagram of our specific model, but they have a common way of being built up as models. So this type of multi-scale models that I will use today are called multi-scale models of nested type. There are a number of different approaches to build a multi-scale model. But this one I will consider today are of nested type, and the nested multi-scale model are actually based on H-structured differential equations. And this is going back to Glenn's talk earlier in the morning. This is one other reason why H-structured models need to be investigated, because they are a vessel for studying multi-scale models. Multi-scale models combine two or more scales, and ours combines only two. This is the within-host scale, the within-host component. And the within-host component, we're looking at a single individual, and we are looking at the number of parasite particles. So these are these blue circles. Sometimes we look at the immune response particles. We do not do that in this model specifically, but it could be the case. And we also look at the target cells. So we model the dynamics of the parasite, which in our case is HIV virus, and the target cells, which in our case are the CD4 cells, and the infected target cells or the immune response. This is on the within-host scale. On the between-host scale, this is a population scale. This is what Glenn modeled this morning. He was talking about number of individuals in all cases. We have susceptible population, at least in the simplest possible scenario. Our model is much more complicated. It has multiple classes. But in the simplest possible scenario, we have a susceptible population that gets infected from the infected population and becomes infected. And what happens between the scale is that each infected individual is structured with time since infection, and it is structured with this within-host model, which is parameterized by the time since infection. So I will demonstrate that in a minute. So this is the actual diagram of our between-host model. Remember, we are going back to having HIV and having opioid addicted individuals and individuals who have both HIV and opioid addiction. So as the S class denotes the susceptible individuals, and they're recruited at a rate lambda and die at a natural death rate mu. And susceptible individuals can become opioid addicted. U is the opioid addicted class. At a force of infection lambda U of T, I will introduce the form of the force of infection on some of the next slide, and become opioid addicted. Opioid addicted individuals can get treated at a rate delta U and go back to the susceptible class. So they drop the opioid addiction and go back to the susceptible class. While opioid addicted, they die from natural causes and disease-induced death rate called DU. And they may progress at force of infection lambda V, which is the force of infection of HIV. So opioid addicted individual, if they get HIV, they go to the co-affected class, where individuals are both opioid addicted and have HIV. And that happens at some rate QV, lambda V, where QV may or may not be smaller than 1. It's just a parameter. Also, susceptible individuals can get HIV at the force of infection lambda V and become HIV-infected individuals. HIV-infected individuals, as you probably well know, do not recover, but they can progress to the co-affected individuals if they become opioid users at the rate QU lambda U. This is the force of infection. And they move to the co-affected class. And if they move to the co-affected class, co-affected individuals can be treated at a rate delta U times sigma to go back. Once infected with HIV, all they can do is go back to the HIV-infected class. The HIV-infected class, individuals die at the rate DV and progress to the AIDS class at the rate gamma V. The co-affected individuals die at a natural death rate mu and a disease-induced death rate DI, and progress to the AIDS class at the rate gamma I times I. And individuals in the AIDS class die at a disease-induced death rate DA. So this is the between host component of the model. So this is this part for our model. So on the next couple of slides, I will introduce the forces of infection. So this lambda U here and lambda V. Lambda U is the force of lambda V is the force of infection of HIV, and we assume it to be a constant times the number of HIV-infected individuals plus time since co-infection structure. So tau is the time since co-infection structure function beta V2, multiplying the co-affected individuals and integrating over all co-affection classes, divided by n. N is the total population size, which is a sum of S plus U plus V plus the integral of I. The AIDS individuals are not included in N by our assumption. The force of infection of opioid addiction is some constant coefficient beta U times the total number of opioid addicted individuals, which comes from those who are only opioid addicted or those who are both opioid addicted and HIV infected. And this is some or integrated with respect to the tau variable, which is the time since co-affection. So the full model takes this form. Susceptible individuals are recruited at the rate lambda. They can get affected by opioid addiction and move to the opioid class U at the rate lambda U, or they can get affected or infected by HIV at the rate lambda V and move to the HIV class V at this rate. They can die from natural causes, or those individuals who are opioid addicted may get treated and revert back to the susceptible class. The opioid addicted class increases by those susceptible individuals who become opioid addicted. decreases by those opioid-addicted individuals who get HIV, and those move into the boundary term, so they move to the term with time since co-affection equal to 0. And then they can die from natural causes, from disease-induced causes, or get treated and become susceptible again. HIV-infected individuals increased by those susceptible individuals who have been infected with HIV, and decreased by those HIV-infected individuals who have become opioid addicted, and those HIV-infected individuals who have become opioid addicted move to the co-affected class at the time since co-affection equal to 0, so as a boundary term. And the HIV-infected individuals die from natural causes mu, disease-induced death rate DV, and at rate gamma V, they progress to the AIDS class. And they are also increased by those co-affected individuals who are treated at the rate delta U times sigma and move back to the HIV-infected class. The co-affected individuals are structured as a PD. This is what first order PD, this is what Glenn was talking about. So he sort of did the groundwork for me. So we have a derivative with respect to time, T, chronological time, and derivative with respect to tau, which is the H of co-affection. And this is the rate of change of the co-affected individuals in both of those variables. And that decreases at the natural death rate mu, at the disease-induced death rate DI, at the rate of progression to the AIDS class gamma I, and at the rate of treatment of co-affected individuals for opioid addiction, and they go back to the, when treated successfully, they go back to HIV infected only. And the AIDS class increases by those HIV individuals who have progressed to the AIDS class, and those co-affected individuals who have progressed to the AIDS class, and decreases by the natural death rate and the death rate of the AIDS class DA. So as you can see, this is a pretty serious model. It has 1, 2, 3, 4, maybe 5, 6 equations. So now I introduce the within-host model. The within-host model is a very simple HIV model, which has been around for a lot of years. It has been expanded to include the opioid drug concentration C of tau and the impact of C of tau on the average susceptibility of the target cells. So the within-host model, remember I told you the within-host models model the interaction of the virus with the cells inside the body. So we have the target cells T. This is happening with the H since co-affection. And they are recruited at the rate S, cleared at the rate DT, and target cells get infected by the virus, which is denoted by VI, V sub I, at the rate K, which depends on the concentration of the drug in the blood, Kc. And once infected, they go to the infected target cells. And the infected target cells increase by this same term, but decrease by the rate delta I with which they are cleared or die. And the target cells, for the equation of the virus, the target cells produce new viral particles at the rate pi. and the virus is being cleared from the body at some rate we call C. And the equation for the concentration of the opioid is a very simple equation. So the rate of change of the concentration is increasing by the dosage. This is the dosage which sort of we are approximating by being a continuously infused dosage, even though it is regularly taken in at intervals, but that will result in impulsive differential equation. So we decided to simplify it and take a continuous dosage. And the opioid drug concentration is declining at a rate DC. So we have these two models. This is the between host model, and this is the within host model. And I have to tell you how they're linked together. So KC is the rate of infection of the target cells by the virus. Has the form in terms of C a constant times C over C plus another constant. So beta 1 and C0 are constant. C0 is half saturation rate and beta 1 is maximal saturation. And besides that, I have to tell you how the between host model and the within host model are linked. And we have several in the between host model, particularly in the forces of infection. We have a couple of functions that depend on tau. This is BV2 of tau. And also DI of tau, gamma I of tau, and sigma of tau. And these functions depend on tau through the within host model in the following form. So BV2 of tau is just a constant times the viral load over another constant plus the viral load. Gamma I is a constant times the viral load. The death rate of co-affected individuals is a constant. The target cells at 0 minus the target cells at tau plus D1. And sigma tau is just taken to be a constant. So the complete model consists of the between host model, the within host model, and the linking functions. So this is the complete model. So you can see that complete model has what, somewhere like 10 equations, and we had to parameterize that. Our main model cannot be parameterized from the literature. Thus, we use fitting to data to parameterize the model. For the within host model, we have data on the viral load and the CD4 cells in monkeys treated with opioid. Monkeys infected with HIV and treated with opioid, actually simian, but similar. And for the between host model, we use various data sets for the population level of HIV from the United States. So we use data on HIV diagnosis, HIV deaths, and opioid deaths. So we fit a total of 5 data sets. So nested multi-scale models can be fitted in 2 ways. We call the first one sequential fitting. In this, in a sequential fitting, we first fit the within host model to the within host data set. We fix the parameters of the within host model, and then we fit the between host model and the between host parameters to the between host data set. Alternatively, a different approach is to fit simultaneously. That means we fit simultaneously the within host model and the between host model to all 5 data sets that we have. So our preference is to fit simultaneously because our prior research has suggested that this leads to better identifiability of the parameters. And here are some pictures. So here, these are This is the viral load, and the pale red maybe points are the data of the viral load. So you can see that the agreement is pretty reasonably good. And the second picture is the CD4 cell count. Again, the red dots are the data points, and the blue curve is the solution of the model. And again, the agreement is pretty reasonably good. For the between host data sets, so this is the number of AIDS diagnoses in the United States in the period 2000-2018. The gray bars are the data. So the datum is actually the middle of the gray bar. And what would you call that? Orange curve is the solution of the model. You can see that the fit is not perfect, particularly in the last few years, but it is still fairly good and captures the dynamics of the data. The number of deaths due to HIV, the data are again the gray bars. This is from 2008 to 2018. The data kind of stabilize starting in 2011 maybe, or 12, kind of stabilized, but our model is still declining or projecting a declining number of deaths due to HIV. So this fit is a little bit worse. And finally, the fit of the number of deaths due to opioid overdose. These are the data I showed you, but here we stop at 2018, simply because the research was done early on. And the data are again the green bars, and the orange curve is the solution of the model. And the agreement is again pretty reasonably good. Again, the last years is worse compared to the first years. So now I will introduce the multi-scale model with controls. So, we use 4 controls. U1 is the control variable corresponding to treatment of the opioid addicted individual. So each delta U is multiplied by U1. And U2 encompasses control measures that reduce the HIV risk behaviors in drug users. We were particularly interested in this particular control because it has the ability to decouple the epidemics. This one is incorporated as 1 minus U2 at every term where opioid addicted individuals can get HIV, so together with QV. And then we have controls U3 and U4. They act on within host level. So they both mimic medications that are being used to prevent HIV infections. So U3 mimics medication that kind of like entry-level entry inhibitor prevents the fusion or prevents the virus from entering the target cell. And U4 mimics medications that prevent the infected target cells from producing viable viral particles. The objective functional for the control problem is given by this expression. A1, A2, and A3 are just constants or weights. So our objective is to minimize the number of opioid users, the number of HIV infected, and the number of the co-affected individuals. And here are the controls. We want to minimize, if we think of the controls as the cost, minimize the cost of applying those controls with constants B1, B2, B3, and B4. The optimal control problem that we are solving is find control quadruple U1, U2, U3, U4 that belongs to the control set U, such that the objective functional at the optimal control is actually the minimum of all values of the objective functional. And the control set is given by this expression here. So U1, U2, U3, U4 belong to the space L infinity squared by L infinity squared. U1 and U2, because they act on between host level, act from 0 to some final chronological time, which we call TF. And their output is bounded between 0 and UI max, for I being 1 and 2. And the controls U3 and U4 act from 0 to some endpoint for the time since coaffection, tau f, and their output is bounded between 0 and uj max, where j varies between 3 and 4. So this is the control set. So this is the objective functional that we were trying to minimize. So now we considered 6 optimal control scenarios. Scenario A, so we considered those scenarios by setting some controls to act and some controls to be 0. So some controls are on and some controls are off. So in scenario A, only control U1 is on. So that means we are treating the opioid addicted individuals for opioid addiction, and all other controls are off. So we are not treating for HIV. We are not disturbing opioid addicted individuals getting HIV or anything like that. So all other controls are off. So these are the results of scenario A. You can see now here, the blue curve is the curve with control, and the red curve is the curve without control. So you can see that this treatment increases the number of susceptible individuals, which is good, decreases the number of opioid addicted individuals, which is also good, but also increases a lot the number of HIV-only infected individuals. So that's what this control does. We believe that happens because the two diseases are in some sort of competition. So if one of them is suppressed with the control, the other one takes off, which is what we observe here. Co-affected individuals are also decreased, which is good. And this is the profile of the control. Basically, the control has to be set to the maximum level specified and stayed there. Control scenario number 2, or control scenario B. In this control scenario, control U2 is on and all other controls are off. So U2 is the one that reduces the transmission rate of HIV to opioid affected individuals. And the results of this control scenario, we have little impact on the susceptible individuals, actually no impact on the susceptible individuals, and little impact on opioid addicted individuals, which are actually increased by the end of the time span. Little impact on the HIV infected individuals. So this control has its main impact in decoupling the epidemics, mainly reducing the number of co-affected individuals. So there are a lot fewer co-affected individuals with the control than without the control. And the control, again, has to be set at the maximum and stay there for the entire duration. Control scenario 3, C, we use control U3 is on and all other controls are off. U3 is like an entry inhibitor, a medication used for HIV, so it acts on within host scale. It has little impact on the susceptible individuals and little impact on the opioid affected individuals, since this is an HIV-related control, but it decreases quite a bit the number of HIV-infected individuals and also decreases the number of co-affected individuals. The control profile is a bit interesting. It has to be 0 at the first 20 units, and then at maximum for about 40 units maybe, and then goes back to 0. Control scenario D. Now, the remaining control scenarios, D, E, and F, incorporate multiple controls. So in control scenario D, control U2 and U3 are on, and all other controls are off. So U2 is the one that obstructs opioid-addicted individuals from getting HIV, and U3 is a within-house control that it's an entry-level inhibitor, for instance. The results, again, little impact on the susceptible individuals. Actually, the opioid-addicted individuals increases, but very slightly. The HIV individuals decrease somewhat. This is a substantial decrease relative to everything we got. And the co-affected individuals decrease even more substantially. And the profile of the controls, U2 has to be at maximum for the entire time, which is 80 units, I think. And U3 has to be on and off, just as when acting alone. Control scenario E. So in this control scenario, controls U1 and U2 are on. So these are two between host controls. U1 is the one that related with the treatment of opioid-addicted individuals. And U2 is the one that does not allow opioid-addicted individuals to get HIV. So from the results here, we have a relatively significant increase in the number of susceptible individuals, relatively significant decrease in the number of opioid-addicted individuals. Again, the HIV-only infections take off and increase substantially, and a significant decrease in the co-affected individuals. And I believe both controls must be on the maximum for the entire time. And the final control scenario is control scenario F, in which all 4 controls are on. We had to investigate this one. If we have 4 controls, what's the point of not looking at this scenario? Here we have interesting results. So there is the number of susceptible individuals is increased. The number of opioid-addicted individuals is decreased. The number of HIV individuals has decreased up to time unit, I don't know, 18 or so, but then it is increasing again long term. And the number of co-affected individuals is significantly decreased. And the control profiles are kind of very, very complicated. So control U1 is the blue, and it is stuck at maximum for the entire duration. Control U2 is with red, and again stuck at maximum for the entire duration. Control U3 is a within-house control, and it has this strange pattern of being off and then on and then off again. And control 4 is the last within-house, the other type of medication. That one has similar off-on pattern. It is off the first 20 time units, on at a maximum the next 90 units, up to unit 90, and then it goes to 0. So in summary, We formulate a multi-scale model of HIV and opioid addiction. We fit the model to 2 datasets within-host datasets and 3 between-host datasets, so a total of 5 datasets. The model has approximately 10 equations. We formulate an optimal control problem with 4 controls. 2 control functions, U1 and U2, are on the between-host level, and the other 2 control functions, U3 and U4, are on the within-host level. We considered 6 optimal control scenarios by setting some of the controls equal to 0. So strategy A, or optimal control scenario A, only uses U1, and strategy E only uses U1 and U2, and strategy F uses all 4 controls, lead to increase in the HIV-infected individuals. So every time U1 is on, apparently, we see increase in the HIV-infected individuals. All strategies lead to decrease of co-affected individuals, but this effect is more pronounced with strategy B, which uses U2 only, strategy D, which uses U2 and U3 only, and strategy E, which uses U1 and U2, and strategy F, which uses all controls. So every time we have control U2, which is there to prevent the opioid addicted individuals from getting HIV, we see a significant decrease in the number of co-affected individuals. Direct comparison of all strategies suggests that the best strategy is strategy F, not surprising, with all controls applied. This means that treating HIV-infected individuals and opioid-addicted individuals has to be coupled with control measures that reduce the propensity of opioid-addicted individuals to get HIV. In some of our prior studies, we have found that the best strategy is a strategy that uses control U1 and U2 only. But in this study, we have modified that, and that makes sense. We need not only to treat opioid-addicted individuals to prevent opioid-addicted individuals from getting HIV, but we also need to treat the HIV-infected individuals to be successful. And this work was supported by an NSF grant, and the talk is based on 2 articles. They're both published, and they're joined with, in different combinations, Necip Tuncer. If you have questions to her, she can answer them. She's right here. Cherny Gupta and Eric Namford.